Here at the University of Birmingham, we have an amazing team of paleontologists from all over the world researching all types of ancient creatures, from the biggest dinosaurs to the smallest microscopic algae. With our friends at the Lapworth Museum, which is just next door to us, we all work together to try and answer important questions, whether that's what the oceans looked like in the past or how climate change impacted ancient animals. In these videos, you can meet some of our paleontologists, and we hope you learn something cool today.
Hi, I'm Andy, and I'm going to show you a few weird and interesting crocodile ancestors from the geological past. But before we go back in time, let's take a look at a couple of very different crocodiles that are alive today. This is a 3D print of a skull of Crocodilus porosus, or the saltwater crocodile. The skull is much smaller here than it would be in real life. The saltwater crocodiles are the world's heaviest reptiles, weighing more than a ton, and they can grow to up to 7 meters long. They also have the strongest bite of any animal, producing up to 1.6 tons of force. This skull, on the other hand, belongs to Tomistoma schlegelii, or the false gharial. It can grow up to around 5 meters long, and actually lives in some of the same areas as the saltwater crocodile. So it's still an absolutely massive animal, but its skull is very different. Instead of the very wide skull and really robust lower jaws of the saltwater crocodile, its skull is much more thin and fragile. The saltwater crocodile skull is designed to withstand huge forces that might be produced in its death roll and head shaking to tear off parts of its prey to eat them. But this wasn't the case, or isn't the case, with Tomistoma. Now, why would this crocodilian have a weaker skull? Surely stronger is better, right? Well, to explain, I need to get these crocs back into their natural habitat. You're generally not going to find many crocodiles living in your kitchenware. They do live in water. Crocs are semi-aquatic, meaning they spend time both on land and in the water. And a big part of life is eating, which crocs mainly do in or from the water. So let's see what happens when these crocs do a big bite in the water. So we'll do Crocodilus porosus first. Okay, that's a pretty big splash from that. And now we'll try Tomistoma. Okay, much smaller splash. So what can this tell us about the diets of our two modern crocodilians? Well, it's all about water resistance, the force you can feel when you move your hand about in a bowl of water. So you can try this at home, probably in the bath to avoid a mess. Take one finger and move it as quickly as you can through the water. And now take your entire hand and move that as quickly as you can through the water. Okay, so unless you've broken the laws of physics, your single finger will probably have been quicker and more easy to move than your entire hand. And it's this exact reason why Tomistoma has an easier time catching small and nimble prey, like fish, for example, whereas the saltwater crocodile goes after maybe larger prey. Now, in reality, it's a little bit more complicated, as both of these crocs are generalists, meaning they'll eat whatever's available. So if it has to, Tomistoma might go after larger prey, but with a more fragile snout, this might be more risky. Likewise, saltwater crocodiles do eat smaller animals like fish too, but as a general rule of thumb, skull shape can be really useful when we're trying to work out the lifestyle of fossil animals. For our first croc ancestor, we're back in the latest Cretaceous, between 72 and 66 million years ago, when dinosaurs like Tyrannosaurus rex were dominant, and huge sauropods, the long-necked dinosaurs, roamed the landscape. But the croc we're here to see isn't big at all. In fact, it's kind of cute. So this is the skull of Cynosuchus clarki, and this is actual size. It was a pug-nosed crocodiliform that, appropriately enough, was actually about the same size as a small dog. And to be honest, a fair few depictions of this animal are really quite cute. But how did it live? What did it eat? Well, its eyes, which are these holes here, and its nostrils, which are these ones here, are at the sides of its head. So it wouldn't be well suited to floating on the surface or near the surface of water like modern crocodilians. Its tail, when you look at its skeleton, is short, so no good for swimming, and it has long legs. So all evidence points to this animal living on land. As for its diet, its teeth, which we can see here, are actually really similar to those of dinosaurs like Iguanodon, a herbivore. But what else can we see that might have helped it eat plants? Well, its jaw joint, which is just here, moved forwards, and its snout has got a lot shorter. Both of these have an effect on how hard it could bite. I'll show you what I mean. Right, we're going to pretend that this spade is a crocodilian lower jaw, with this hand representing the jaw joint and this arm being the muscles that pull the jaw up into a bite. That end is the toothy end that's going to actually bite, or in this case, just lift a bag of sugar. So with the jaw joint all the way back here, let's see how much force it takes to lift this bag of sugar. So that's about 4 kilograms. Not bad, it's pretty efficient just here. But let's see what happens if we move the jaw joint all the way forwards to here. Let's lift with the same amount of force, about 4 kilograms, and you can see that the bag of sugar didn't move at all. It got a lot less efficient, and the bite got weaker. So let's see how many kilograms it actually takes to lift the bag of sugar when it's just here. So that takes about 10 kilograms just to lift that bag of sugar. The jaw is much weaker and less efficient. But that's not all that's going on. This time, my 2 fingers here are going to take the place of the crocodile's jaws, and I'm going to bite this set of scales as hard as I can. Okay, so I got about 1.6 kilograms there. Now, I've taped some wooden rods to the end of my fingers, making the jaw a whole lot longer. So if I bite now, in the same place, as hard as I can, the bite force is a whole lot less. Why? Well, it's because the bite point is much further away from the biting muscles. Because Cymosuchus had such a short set of jaws, this actually increased its bite force. In fact, it increased it so much that even though its jaw joint was so much further forward, it had a more powerful bite than expected. But if it was eating plants, why would it need a strong bite? Well, the answer is pretty simple actually. Plants can be pretty tough. Compare eating a chicken nugget, for example, to biting on the stick of an ice lolly. Moving on from Cymosuchus to our second croc ancestor, we're going even further back in time to the late Jurassic period, around 170 to 145 million years ago, and we're going to an environment we've not visited yet. We've seen crocs from coastlines, and we've seen crocs from river ecosystems, and we've even seen a crocodile ancestor that lived entirely on land. So now we're going to the open ocean. You might not think of the UK when you think of large crocs, but that's exactly where this, Metriorhynchus superciliosus, would have lived. And its fossils can actually still be found in and around the UK and Europe. Now this skull isn't actually life-size. In reality, the skull of Metriorhynchus has been known to reach 83 centimetres in length. The full size of the animal would likely have been between 3 and 4 metres long, so not as big as the biggest crocs today, but still a sizable predator. In reality as well, the skull wouldn't nearly be this flat. This one is flat because it's been crushed by huge geological forces over the millions of years since the animal died. So what features did this animal have that allowed it to be a successful predator in the sea? For one, if we look at its skeleton, it didn't really have legs. Its limbs have evolved into sort of paddles. Again, in its skeleton, right at the end of the tail, you can see that it bends down. Now, this isn't because it's broken. It actually supported the bottom half of a shark-like tail, exactly the same as another group of marine reptiles that were alive at the same time, the ichthyosaurs. It entirely lost its bony armour plates, which made it much smoother than modern crocodilians, and more streamlined, making it faster in the water. If you go back to its skull, the eyes weren't positioned in the top, like we see in modern crocs, but they were positioned more at the side. There's a really good reason for this. So if you have eyes on the sides of your head, like the majority of animals actually that live in the sea, then you can see both above you and below you. Now that's very important if you're looking out for predators coming from either above, below, or any direction. It's also very important if you are a predator looking for your next meal. Something else you might notice about this skull in particular is the massive holes behind the eyes. What were they for? Well, we've just had a look at how bite forces get weaker as the jaw gets longer. But what also happens as the jaw gets longer is that the end of the jaw moves quicker when the jaw closes, which is great for catching quick prey like fishes. And this is also something that the false gharial here really benefits from. What can you do if you want the advantage of having a quick bite, but also have a really strong bite? Well, you just have to have bigger biting muscles. And that's exactly what these holes were filled with. They were entirely packed with muscle to make sure Metriorhynchus not only had the speed to catch prey, but the strength to hold onto it. As we move even further back in time to the late Triassic, we can no longer really call our next animal a crocodilian, or even a crocodiliform. It's more primitive, or technically speaking, more basal than that. We're going to have to use the more general group name, so this is a Pseudosutian. Right now we're back in the late Triassic, in an area that 213 million years later will become a place called Ghost Ranch in New Mexico, USA. This is a time when crocodiles' distant ancestors, the basal Pseudosutians, dominated ecosystems, overshadowing at the time a small group called Dinosauria. The last animal we're going to look at is Ephigia o'Keeffe, and you'd be forgiven looking at this skull, which is life-size, for thinking that it was a bird. It's got large eyes. If you look inside the skull, it's got absolutely no teeth. And it's got a pointed beak. If we were to look at the rest of the animal's skeleton, we'd see that it was about 2 meters long, and it actually walked on 2 legs. But birds wouldn't evolve for at least another 63 million years, and birds are dinosaurs. This is a crocodile ancestor. Its name, Ephigia, means ghost, which is quite appropriate as this animal is quite mysterious. It's known from very few fossils, and there hasn't been much research into its lifestyle. What we do know is that all fossils we have from this animal are immature, meaning that they weren't actually fully grown. We know that its beak just isn't right for carnivory, or meat-eating. If we look at the beaks of carnivorous birds today, they're hooked to tear at the meat, or sharply pointed. Now this is neither. So what did it eat? Well, there's no real answer, unfortunately. We can speculate, or make an educated guess, given the plants that were around at the time. It might have been using its curved beak to slice through tough plants like horsetails, using its curved beak like garden shears, like these ones for example. You can see the similarity. It might have also eaten the seeds of the ancient ancestor of the monkey puzzle tree, which was certainly around at that time and in the same area. Or it might have eaten the seeds or fruits of seed ferns, which are an extinct group of plants that might have given rise to modern flowering plants. So that's almost as far back as we can go whilst talking about just croc ancestors. If we were to go back to the earliest Triassic, around 250 million years ago, we would find the common ancestors of crocodiles and birds. Now the easiest way to think about this is to imagine a tree with 2 huge branches. Along one of the branches evolved all of the croc ancestors we just talked about, with the modern crocodilians at the very tips of the furthest branches. Along the other branch evolved pterosaurs, dinosaurs, and finally, again at the very tips of those branches, we've got modern birds. Down here at the base, where the 2 branches join, we have the common ancestor of all crocs and all birds. And together, the entire group from the common ancestor to all of its descendants, that group is called Archosauria, or the ruling reptiles. So what do you think the common ancestor would have looked like? Well, maybe you can go and find out on your own. So with that, I'll say thank you very much for joining me, and I hope you enjoyed it and learned some interesting things along the way.